Okay, so today we're going to look at lecture 2 on data, structure, and learning. So in this lecture, we're going to look at various forms of data. Data is probably the most important ingredient in machine learning and AI nowadays. We'll look at examples of visual, language, auditory, sensing, set, and graph data. We'll then generalize all these data forms into a general discussion of what makes data unique, what are the properties in your data, how you should think about your data, and what are the right modeling architectures to design for your data. We'll give examples of real-world data sets, and we'll also talk about labels. Right? Often you have raw data coming in. We're trying to learn some features so that you can label or make some inferences on them. So in order to make these inferences, we'll cover types of label and types of learning paradigms. What are different objectives that you can impose on your methods so that they can actually learn well in practice. Before getting into the lecture, just some logistics. All of you should have been added to Piazza. If you haven't, please let me know as soon as possible after the class. Piazza will be our resource where all the announcements will be made. For example, this first announcement, and also including the links to all the websites, lecture slides, course calendar, syllabus, and so on. So please make sure you are enrolled in Piazza. Emails have been sent out. Probably have to activate and register your account if you haven't used Piazza before. So please do that as soon as possible. Speaking of Piazza, our first announcement is that we have this project preferences form that is due by the end of today. So if you are planning to take the course and do a course project as part of it, please fill out that form. Okay? So that form is a very short form asking for your name, which team members you already have, or if you're looking actively for team members and you need us to help you match students of similar interests together, and also general interests that you have in doing the course project. All right, so please register on Piazza and fill out that project preferences form by today. I also end the lecture a little bit early, so students who haven't found teammates yet have a chance to mingle and find those of similar interests. Another quick area of logistics, we realized that next week, week 3, Tuesday and Monday are actually swapped. If all of you didn't know that, Monday is President's Day, but instead of canceling class on Monday, they're canceling class on Tuesday and moving Monday to Tuesday instead. That seems to be the official university policy. And as a result, everything on Tuesday is canceled. We won't have a lecture next Tuesday. So we have to reshuffle some of the things around to fit more content into these lectures. Okay. This calendar, if you haven't seen it before, is also going to be very useful. It will cover the topics for every week and also any important assignments. So in red, for example, you see the project prefaces. That form is due today, February 11th. And very soon, a very important checkpoint is that next Thursday, not this Thursday, but next Thursday, February 20th is going to be your first proposal presentation. So we're going to send out those instructions for roughly everyone and their teammates who are doing a research project. We'll present for about 5 minutes outlining their broad ideas, different data sets and models that they want to get started with. And the point of it is to get feedback from the instructors and other members in the class. Okay, so just look out for this calendar. It's again linked on Piazza, so please join Piazza if you haven't yet. Several other logistical things. For example, this Thursday, you'll see that there's a PyTorch and Hugging Face tutorial that's going to be led by some of my students. Mostly an introduction tutorial to different tools that you'll be using in machine learning, covering how to quickly iterate on code, use GPUs, monitor your experiments, and so on. And some of you also asked when the first readings will be released. So over here on Thursday, this Thursday is going to be a PyTorch and Hugging Face tutorial. Next Thursday, all of you will be presenting your proposal presentations. And the following Thursdays, with the discussions will start. Discussion 1, 2, 3, 4. 4 discussions before spring break. And that means readings will be released roughly a week before the discussions. Okay, so the first reading will be released on February 19th. All right, so definitely check out the calendar. Okay, jumping into today's lecture. So in machine learning, we often talk about data. Right? Data is key to any accomplishments in machine learning. And you want to think of this data as belonging to some sensory modality. These sensory modalities essentially refers to some way in which data is expressed or perceived in the world. When you look at data, you often think that there's some sensor behind which data is collected. And you can essentially look at data modalities from more raw, which are closer to the sensor, to more abstract, that are further away from the sensor. So raw data, for example, can include a speech signal that's directly collected from a microphone, recording somebody, give me an image directly recorded or captured from a camera. And you can then think of making abstractions from the raw modalities. So for example, you can extract the language, the specific words that a person is speaking from their speech signal. It's making an abstraction by keeping some information and throwing some other information away. You can then start detecting objects from images. Again, that's a form of an extraction, extracting out what objects are there, what locations there are, while throwing away some other parts of the image. And you can go even more abstract, right? From language, you can detect somebody's sentiment, whether they're feeling positive or negative about the topic that they're speaking about. From detected objects, you can extract the exact object categories. So machine learning and AI is mostly about learning these abstractions, going from raw data, which is often very high-dimensional, noisy, unclean in the world, to learning useful abstractions and making inferences on that data. So the whole lecture and the whole point of the course is to cover what forms of data there are and what are the right ways to learn these abstractions that are useful for some task that you care about. So to see some of that in practice, well, all of you have probably seen visual modalities. Here's a color image. And when you look at these modalities, they often have to be represented in some way on your computer, right? So images that you might want to classify will be represented as pixels, where you have a height, you have a width, and each dimension has some channels, so number of colors, RGB behind them. So it's usually a three-dimensional matrix, height, width, and channels. And from these images, you can classify the presence of an object. You can also classify, that can be posed as a binary classification problem. So whether there is a dog or there isn't a dog, you can also pose it as a multi-class classification problem. So you might have a large set of categories that you're trying to infer from the image, and your goal is to choose one of the right categories. Okay, so that's an example of visual data and some of the inferences you might make on visual data. Language data, you can get lots of language data on the internet. Here's some written language on Amazon, for example, that somebody might have written after purchasing an item. And you can also get spoken language, for example, actual recordings of people speaking in movies or TV shows. Another good source of data. So from language data, you could try to infer, for example, a sentiment, whether a particular word that appears in the whole language data, for example, the word humorous, can that be inferred as positive or negative? Again, how would you represent this data? Humorous, it's a string on your computer, but how would you represent it in a way that can actually be taken in by your machine learning or AI algorithms? Well, bag of words is one simple way of doing it. This bag of words, what this essentially means is that you first collect a dictionary of all the words that appears in a sentence. So multiple words, and you're essentially putting an index 1 if that particular word is of interest. So humorous is that 8th word in the dictionary. You're going to put an index 1 at the 8th position and 0 everywhere else. So that's an easy way of representing the words in a digital format that your computers can take in. So you could classify, for example, these words, whether it's positive or negative. You could classify what part of speech it is. Is it a noun, verb, adjective? You can also classify whether it's a named entity, for example, whether it's a particular location or a particular object. And nowadays, of course, we don't really train word level models. We train sentence or paragraph level models. So you might take in multiple words in a paragraph or in a dialogue, and you're trying to make some inferences on it, whether the whole paragraph indicates that a person felt positively or negatively about the object that they purchased, whether this whole paragraph can encode it in a model and generate a response. So the customer agent might automatically respond to this review that a person wrote. So these are more sentence or document level classification tasks. And easy ways of representing it. You can continue using your bag of words. You will basically just count which words appear. So maybe the word ideal appears, that's the 2nd token in the dictionary. The word anyone appears, that's the 5th token. The word humorous appears, that's 8th token. and essentially putting a 1 on all the words that appear in the dictionary in your sentence and 0 everywhere else. That's again a way of representing your data. Of course, all of you might realize that these are very simplistic ways of representing your data. For example, a bag of words, just counting which words appear, doesn't really deal with the ordering of words. For example, not happy, these two words, one after the other, actually mean something very important versus happy, blah, 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 not somewhere else. So of course, we're going to look at more examples throughout the course on better ways of representing your data and better ways of learning from your data. But again, this just meant as an introduction to various forms of data. So we saw vision, we saw language. Audio is another common modality. Sometimes you might obtain acoustic signals from a microphone, and usually these signals are discretized in some way because these microphones are sampling at some fixed frequency from the continuous data in the world. So again, from this audio signal, you might try to infer what the person was speaking. That's a task of automatic speech recognition. And there's several key parameters for audio data. For example, what the sampling rate is. So how often you're recording the person at a frequency. What is the bit depth? How much are you recording for each sample? And also other things that you might want to consider. For example, what is the time window? What is the time window in which you want to recognize what word was being spoken? Right? If you put your time window too short, you might only hear a particular phoneme, so a particular character that a person was saying. If you put your time window too long, then you might recognize more than just a word. You might start recognizing more things, and your model may not be as precise in measuring words. Different ways of, again, representing audio modalities. This is basically a time dimension representation. You might have also heard of spectrograms, which essentially transforms the time dimension to a frequency dimension, frequency and amplitude. So spectrograms are another way of representing audio. People have found, surprisingly, that you can treat the spectrogram as an image and even give it to an image recognition model to make inferences on spectrogram. So there's some relationship between audio modalities and visual modalities. Okay. So again, you can start recognizing audio by essentially putting input observations from the first time step with some fixed time window and with the next time steps with some other time window, and use that to recognize things in audio. Naturally, you can recognize spoken words, but you can also recognize emotion, whether someone seems to be feeling positive or negative, not just from the words they're saying, but the way they say it, maybe the magnitude and amplitude of their voice, and also how fast or slow they're saying things. And you can also see what the voice quality is. So that's an audio modality. Sensing modality. So if you're working with robots or environmental sensors, you often collect data across time. So you're measuring some particular physical phenomena across time, and on the y-axis, you're showing how that sensor varies. So over here, this is an example of a force torque sensor that is often applied on robots, where you're sensing across time, and each dimension is some 6-axis force torque sensor. So it's measuring the force across 6 different components. Often when you work with robots, you also have some internal proprioception data. A lot of these embodied systems have some internal states within them. These internal states might measure where the robot is, what angles the robot arm are, and maybe its speed, velocity, and other parameters that are internal to the interactive agent. So again, this is data across time. So there's a t, there's a time dimension. And in this case, it was just measuring the current position, XYZ axis, and velocity of this robot arm. So it's something like t/2. And with all this sensor data, you can essentially train a model that takes in this sensor data and output something. You can output and try to predict what object the thing is grasping, and you can predict some property of the robot arm. A property of the object that's being grasped by the robot arm. For example, whether it's a soft material, hard material, rigid, different shapes. And you can also try to predict the next actions. So that's the current sensor data. You might try to predict the next action that a robot should take in order to better grasp the object or to better manipulate the object. And that will then give you a new set of readings for the next time step, right? A new set of force recordings and a new set of proprioception readings in the robot. So that covers sensor modality. Again, key idea is that now you have some time dimension. You probably want to plot it to see this time dimension and the magnitude of the force. And that can be used to recognize things in the physical world and also to take actions so you can see new occurrences of this data and maybe take actions again. So that's sensor modality. Sometimes people say sensor, sometimes people say time series. They're often used quite interchangeably. Time series is technically a generalization of sensor data to something that anything that has a time dimension. So financial data also has this time dimension, and you're measuring, for example, how a stock price changes. That's also considered time series, but you probably wouldn't consider it sensor data. So you're looking for models to encode sensor data. You could search sensor models, but also time series models. Okay, tabular modalities. Here I'm showing a mix of both tabular and time series. This is a common data set used in the medical domain. It's called the MIMIC data set. It's two modalities: tabular information about the particular patient. So what their age, gender, ethnicity, previous medical conditions, all these things that you would typically see in a tabular form. And at the same time, you have time series modalities. So once the patient has been admitted into the ICU, what was the ventilation in their blood? What was their heart rate across time? What was their glucose rates across time from when they were admitted into the ICU to when they were discharged? So that together, tabular and time series, can be combined to essentially make inferences on many medical procedures. For example, what their mortality rate is, what disease they might have had as measured by ICD-9 codes, how long they stayed in the ICU, and so on. Okay, so tabular modality is pretty unique in a sense that one of the key properties is that you can essentially interchange, for example, any of these values, right? Whether you put the age and the gender first, age and gender, or you put gender then age, technically shouldn't change how you make inferences on your tabular data, right? So if your model is actually sensitive to the ordering within these values, then you can be in trouble, right? Another common challenge of tabular data is that the data is often more discrete in nature. So gender, there might be a couple of buckets, ethnicity, there may be a couple of buckets. So it's not the type of continuous data that we are used to if you're looking at images or sensors. So there's some challenges working with tabular data. Graph is also another form of data that is quite interesting, but I don't think anybody really mentioned graphs as their favorite modality. So graphs are everywhere. If you look at a social network, for example, you don't want to just make inferences on a single person in that social network. You want to use that person, but also its relationships with other people in that social network. So that's an example of a graph, who these other people are connected to. Economics networks, biomedical networks, that's very common if you're looking at different proteins. You have to look at how the proteins interact with other proteins and which ones it's not interacting with. So that can be posed as a graph. And also things like the internet and so on. So if you look at graph modalities, typically you have a set of nodes. Those are individual points in the graph, and you have edges, essentially telling you which nodes are connected with which other nodes. Several important tasks on graphs. Node classification. So can you classify some property of each node? For example, in a social network, can you classify each person as being more positive or negative, or maybe their political status, right-leaning, left-leaning? That's a property of a node, but you can't just use that node to make that prediction. You probably have to look at other people they're friends with or other pages that they click on in the social network to make inferences on that person. Link prediction. So given two particular nodes, the probability that they might be linked together, for example, given two proteins, the likelihood that they will interact with each other or bind with each other, given two people in a social network, the likelihood that they will be good friends with each other. So those are more classification tasks on graphs. There's also a lot of tasks which involve using graphs as a database of data and using that to improve other things. So if you're looking at, building a question answering system, a lot of these early question answering systems like IBM Watson, which was superhuman at Jeopardy, these question answering games, they had a big access to knowledge graphs of all this kind of common sense knowledge that you would need for these trivia games. And they essentially queried these knowledge graphs, retrieved answers so that they could answer these questions in real time. Nowadays, of course, people use large language models, but there's also lots of work on the hybrid between large language models where the knowledge is stored within these parameters versus explicit knowledge graphs that you might want a large language model to maybe query and retrieve answers from. Social networks for sentiment analysis, and so on. So lots of opportunities in just graphs itself, making inferences on graphs, and also using graphs as an additional auxiliary modality to make predictions on other tasks. Okay, set modality, sets. So set modality shares some commonalities with tabular modality. So you might have some group or some distribution of objects where, again, each of the objects are important. Which objects are in the set and not in the set are very important. But critically, the order of elements within the set is not critical, right? So over here, I might be looking at a bunch of celebrity images. That's a common task, lots of machine learning data sets for those. And you might be trying to classify some properties with what color hair, what color skin, maybe age, and so on. So you might have a set of objects, but whether this celebrity appears first or this other celebrity appears first is not critical. In fact, if your model is sensitive to the order in which these images appear, then your model will not work as well as one that is not sensitive to the order. So given sets, what you can do, you can detect anomalies, right? Figure out which people or which image does not belong in that set of images. You can do set expansion. So if I want to generate more images with a particular property, how do I sample more elements in that set? And we talk about sets. Point clouds is another example. So we saw 2D images, just height and width. Point clouds are essentially 3D versions of that. So it's called point clouds because each point is X, Y, Z. That's why you have this two-dimensional nature. And clouds because you have a bunch of points where the order isn't important, but together these set of points allow you to kind of reconstruct and visualize these 3D objects. So point clouds. Again, so if you're working, for example, with some 3D representation, you will often be represented as point clouds. You might want to do more sampling. For example, I want to sample different chairs in different 3D orientations following this semantic category of a chair. That's an example of a point cloud expansion task. You might want to classify which particular object. You might want to detect anomalies in these 3D objects. That's all tasks on point clouds. So to summarize, set modality also very important. Key difference is that you have a bunch of elements in the set or these points in your point clouds, but the order does not matter. So if you build a model which is sensitive to the order of the elements in your set or the points in your point cloud, then you're essentially not leveraging your data enough and your model will not work as well. Okay? We'll make a lot of these ideas about models working well and not well in the next lecture where we actually discuss the specific models. All right, so that's a quick glimpse at all the data forms that are out there. Completely non-exhaustive, and also the tasks that are out there. So oftentimes, I like to generalize things. I like to come up with a unified framework. So I'm going to call it a modality profile. Given any particular source of data from any modality that you end up collecting, that you end up labeling your data for, it's always useful to think about several dimensions of that modality. So I call that a modality profile. Roughly speaking, it is the unique qualities and structures that are unique to that modality. Okay, so let me show some examples of what dimensions would fall under this modality profile using these two examples, one from the visual modality and one from the language modality. And you can see that these two are correlated. So this is kind of a rough caption. A teacup on the right of a laptop in a clean room is a rough caption for this image. So what goes into this modality profile? How should I start reasoning about the data? Well, one first dimension that is very important is the distribution of individual elements in your data. So I have this image, I'm going to start realizing that one element is the sofa, one element is a teacup, one element is a laptop, one of them is a table, right? Same thing for language. There are some stop words that I might not care about. The, of, in, these are not very important words, but there's some keywords, key elements within my sentence that I care about. modeling. Teacup, right, laptop, clean room, for example. So I'm going to start reasoning about what these elements are and specifically their distribution, whether they're continuous in distribution, whether they're discrete, and what their support is. So what are all possible elements that I have to capture? So in image, it will be those three bounding box regions, and in language, it might be those words. So the first thing that you're going to start looking at is how do you model these individual elements? How do I learn a good representation that actually captures this being a laptop, even though it's partially occluded by the teacup? How do I learn a good representation that actually captures this as being a visual representation of a sofa with all its properties? And same thing, how do I learn the right representations for the elements in language? Okay, so first dimension, the elements, what the distribution is, and how it could potentially represent these elements. So second dimension is that of granularity. We saw what the individual elements are, but now how frequently do these elements occur? On images, you might see a couple of objects per image. Doesn't seem to be very cluttered. Maybe there's like 3 or 4 primary objects of interest. And maybe in the text, again, whether a person is speaking, there might be words per minute. If it's a sentence or a paragraph or a document, is how many words that I might care about. So that will also influence, the granularity will also influence how I subsequently design models that, after having learned representations of the individual elements, compose these representations across their granularity and frequency. So a third key idea, a third key dimension is that of the structure, right? A structure essentially tells me how these elements compose to form higher level information. And we started with this bottom-up process. We looked at these individual elements and represented them and looked at their frequency. But eventually, you're going to learn a representation of the entire image or of the entire sentence or entire paragraph. So the structure essentially tells you how these elements should compose to get higher order meaning, to form higher order abstractions. So in image, it's often a spatial structure, right? We're looking at elements of images in relation with each other spatially, right? The chair is in front of the table, the teacup is on top of the table, the laptop is on the left of the teacup, and so on. It's a very spatial arrangement, and you should take into account these spatial relationships when you're composing these elements to form image representations. For language, depending on philosophy, some people think language should be composed hierarchically through a grammar, where you have to first look at a teacup, that's a noun, and I don't know what DT stands for, but some precursor to the noun, the right of something. Some people think that language should be composed by looking at words and hierarchically composing them to form higher order meanings through some grammar. So there's been lots of work in, for example, building neural networks that respect this grammar. Very Chomsky way of thinking about things. Of course, nowadays, people know that empirically what works best may not be exactly to respect all this grammatical structure. You can just simply treat it as sequences, maybe one sequence, and use something like a sequence model, transformer, LLM, and that can work well. Same thing for other things. If you have a graph or a tree, there might be some certain structure in which your elements are composed to form more abstract representations. And that's something you should design your model with respect to. Okay, so that's structure. So you looked at the individual elements, how we can represent them, the frequency of those elements, and how these elements combine, what's the structure of combination. Oftentimes, we also care about the total information, the total information in your modalities. So this, once you combine them to form more abstract, high-level representations, what information does it provide? What inferences can I make on these images that I care about? What inferences can I make on the sentence that I care about? So naturally, some modalities would have more information than others. Naturally, some modalities will have more information than others. And oftentimes, these modalities can also overlap in the information that they have. Okay? And lastly, one dimension that we typically don't think about, but it's also very important, is that of noise. When you start collecting these modalities from some sensor, they're often going to be imperfect. So cameras are going to be prone to jitters and shakes and occlusions. Language, if it's being typed on a computer, is going to be prone to various typos. If it's being spoken, it's going to be prone to different mistakes that people make when speaking. And there's often a unique pattern to this types of noise. So thinking about what types of noise could potentially occur in your data and also actually occur in your data is also a very another important dimension when you collect it and work with it. Okay, so this is a summary of various forms of data, non-exhaustive, and also a general view of different profiles, different dimensions that is often very useful to think about when you start collecting data. What the elements are, so that's just one element in your data, their distribution and frequency, how this structure emerges when you compose them into higher level abstractions, different forms of information, whether there's noise or imperfections and what those are. And also, I didn't really cover this, but how relevant it is to the task that you care about predicting. Okay, so that's data. So now that you have data, we have to talk about learning, right? How do you learn from data? And I'm borrowing some slides from Introduction to Machine Learning here that I'm also teaching this semester. But there's generally 3 types of learning paradigms at a high level. Again, these are non-exhaustive. They also overlap with each other. So there's things in the middle, and they're constantly expanding. But it's usually useful to think about 3 types of learning objectives: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning essentially means that there is some supervision for your data. So raw data comes in. Supervision usually comes in the form of some labels, something that you want to predict from your data. So you might have a bunch of images, and you have labels for what objects are inside those images. Cat, dog, table, person. Pretty easy. You might have a protein structure, and you have some labels on which proteins it interacts with or which proteins it binds with. You might have a sentence in one language, for example, Spanish, that's your input data, and you might have label for what is the corresponding translation in some other language. So all these are examples of supervised learning. You have data X, you have labels Y, you're willing to provide that supervision. How do you learn from it? Unsupervised learning is different. So basically meaning no supervision. So now you have data, but you're not willing to provide the supervision in collecting the labels because maybe annotating the data is expensive or requires lots of human labor, or the labels themselves may be very subjective, like a person's emotion may be very subjective. So then you might want to do unsupervised learning where you only have the data X and you're hoping to learn some features that might eventually be useful for labels that you're willing to collect or for some other tasks. So several types of unsupervised learning. You might just care about reducing your dimension, visualizing your data in lower dimensions. Doesn't require a label, just can be done with your data. So can you visualize words? These are called word embeddings, and they have some nice structure because certain countries are grouped together, certain words are grouped together. You might want to train generative models. So if you have lots of protein data, but you don't have labels for what these proteins are or how they interact with other proteins, you can still learn a model that essentially estimates the distribution of your proteins and maybe generate more of them. And we've also seen that for images, right? You have a ton of images. You don't want to label the fact that there's some dog inside. You can still take lots of images and train a model that is able to generate new images. And of course, nowadays, unsupervised learning and supervised learning have really intersected with each other with this idea of self-supervised learning. So you might have lots of data, unsupervised, no labels. Labels are too expensive, but you can still define some good training objectives on your unlabeled data to learn these abstractions, these features that can be then transferred or fine-tuned where you have some little amounts of labeled data and supervised learning. So there's some intersection between them. One example is this, right? These are images of dogs. If you're successfully able to learn the distribution of all the dog images and generate new dog images, then those features are likely going to be very useful in predicting and identifying dogs images. Okay? Third learning paradigm, reinforcement learning. Well, supervised and unsupervised learning typically looks at tasks that involve a single step. So you make a prediction and you're done, or you generate another sample and you're done, or you visualize your data and you're done. Reinforcement learning looks at problems that often occur across multiple time steps. So games are a good example of this. If you want to train a system that is interactive, that can play a game like chess and Go, then there's usually some state of the game, for example, the current state of the chess pieces, some actions that you're taking, for example, playing a particular move, that transitions into a new state of the game, with a new configuration of chess pieces, in which you might want to take another action, and so on, all the way until you've won the game. The key difference in this multi-step process is that we can no longer maximize and choose the best action at a local step. There might be many cases where you take suboptimal actions in the short term to gain longer term better actions in the long term. So that's one of the biggest challenges in reinforcement learning. How do you perhaps forego short term for actions to get long term really good actions? We've seen them in games, we see them in robotics, and nowadays we also see them in large language models. Right? You can think of these large language model interactions with humans as some multi-step interaction where you might prompt it, give you an answer, you prompt it again, give it some answer, and this dialogue across multiple steps. And your goal is to really maximize your long-term reward. So there's lots of work, as you might have seen, on applying reinforcement learning methods in order to maximize long-term interaction quality between humans and LLMs. And we'll cover some of that in the class. Okay, these three might be pretty trivial. Some of you might have seen them before. More learning paradigms that I also want to quickly cover. These are very useful as you start looking at your course projects and thinking about what forms of data you can collect so that it fits into one of these current ways of learning from data. So we saw supervised learning. X comes in, model predicts Y. So you need data that contains both X and Y, paired and labeled data with X and Y. Of course, this is a multimodal learning where you have multiple X's that come in, each of them providing complementary information, and you might make some inference on Y. This, of course, gives you more information that X1, X2 are chosen well, but now you need data with X1, X2, and Y, right? So there's more requirements on the data that you need, and oftentimes lesser data. There's also multitask learning, where X comes in and you predict Y1 and Y2 together, leveraging the fact that two tasks are complementary. So for example, you might want to predict the emotion of a person, but also predict the stress of a person. These two tasks are very often related to each other. You might want to predict, if you're working with robots, some properties of the object, and also taking next actions to manipulate the object. Again, those two tasks, although one is a label and one is the action, are related to each other. So multitask learning, if it works well, can work really well. Of course, limitations is that now you need X and Y1 and Y2 together, right? Data and both labels together, which again could limit the amount of data that you have. Transfer learning is slightly different. So you might train a model X on your first task to Y1, train that model, and then take that model that you've trained and transfer it to the second task. So continue training that model on the second task, Y2. So slightly different from multitask learning, because now you're doing things in two stages. And for the first stage, you need X and Y1 data. For the second stage, you might just need X and Y2 data. Also very common, this two-stage process is particularly useful when you have an unequal distribution of Y1 and Y2 access. So let's say you might train an image model to classify natural images. You can get tons of that data from the internet. You can get tons of labels of natural images. But then I want to transfer it to some medical image collected in the hospital. So you're going to have much less medical images and medical labels. So transfer learning allows you to deal with that asymmetry. Cross-modal learning is kind of the extension for different modalities. Sometimes it might be very helpful to train X1 modality for Y and transfer it to X2 modality for Y, or maybe a slightly different Y. So cross-modal, the input modalities are different. And when you're doing this idea of transfer learning. Nowadays, X1 could be language. You train LLMs for some tasks. And surprisingly, these LLMs don't just transfer to language, they can also transfer to code, to math, to protein structures, to genomic sequences, even to sequences of robotic states and actions, even to game states. They transfer well to a bunch of things, right? So how can we push the limits of cross-modal learning? Okay, so different modalities, and you're doing this transfer. Of course, you can combine this. You can do cross-modal, so modalities are different, and also transfer. So the tasks are also slightly different, as long as there's some relationship between them. Okay, unsupervised and self-supervised pre-training, also very common. It's an extension of transfer learning, where instead of training your first model in a supervised manner from X to Y1, you're doing some unsupervised learning on your first model. So X to X prime. X prime, so in this case, you see that in this first step, you don't need any labels, all you need is X. And X prime is in effect this, self-supervised label that you've created. Several ways of doing that. You can use the left half of an image to predict the right half of an image. You can break your image into different parts and like a jigsaw puzzle and have the model recreate which puzzle parts should go where to recreate the full image. You can use, the first 5 words to predict the sixth, seventh word, autoregressive generation. You can rotate your image or add noise to it and try to remove that noise or unrotate that image. So lots of ways, as long as there's some relationship between X and X prime that you can do automatically, do it on your computer, then you can essentially have unlimited access to pairs of X and X prime so that you can pre-train your model. Okay, and then usually those features, if designed well, are going to be very strong because firstly, you have lots of data. There's a lot more of X data than X, Y label data, so you can leverage lots of data. And if your features and your X to X prime is designed well, then it actually learns very good features that can then be transferred to some task Y. Okay, so we call that unsupervised or self-supervised pre-training. Any questions so far? Yes.
So in the reinforcement learning, you mentioned LLM. So my question is for LLM, right? So you mentioned it often involves multiple steps, right? With human and interactions. But isn't the goal of LLM to generate one great answer? That's why we have the RLHF, right? To make the answer great in one round, rather than having back and forth communication with LLM. Also for the LLM, right? In order to So for the reinforcement learning, we have the objective functions, right? But for LLM, there's no objective function. We don't give feedbacks, right? Like, oh, this is great, but one is horrible, -1, right? So do you think in the future LLM should have an objective function, and then that would involve multiple steps in order to achieve the overall objective?
I mean, great questions, and we'll discuss this much more when we look at LLMs. But I think short answer to your question, of course, you want to maximize the best response that you get in one step, but oftentimes, when I say interact with LLM, I don't mean asking clarification questions, right? If you ask a lot of clarification questions to make it multi-step, that's not good. But oftentimes you get a good answer, you keep talking to it. So there is going to be some natural long-term interaction, which you can model using reinforcement learning. Again, reinforcement learning can be one response, but where each of the steps are one word, and the whole response can be treated as an RL multi-step problem. It can also be multiple responses, each of them treated as one response, one immediate response. That also gives you a multi-step problem. And for rewards, there are tons of work where people rate good, bad, or evaluate the quality of LLM outputs, and all that human supervision goes into the reward function to better fine-tune these LLMs. So that's also very common. Of course, it'd be great if some of these metrics are automatic, but most of these current methods like ROHF still relies on some amount of human supervision and human feedback. Okay? Yeah.
One question regarding the self-supervised training. So the model that is trained in the first step without labels for the second step, is it just using the same block, or is it also including like adding other blocks at the end or in conjunction for the second step?
I've seen all of them. So you can be most of the block. You probably want to keep most of the block if this is a big model. But once you bring it here, you might train a separate linear classification head. You might adapt some of the final layers of the model. You might do low rank adaptation. So there's tons of ways. But as long as you kind of pre-initialize it well and you bring it over, then with some minor adjustments to it. Okay. The hope is that you just do something minor, right? You don't have to retrain the entire model, fine-tune the entire model. Okay, more interactive learning paradigms. So that was mostly just non-interactive making predictions, but interactive learning paradigm. So we saw RL, where X, your data, or in RL, we usually call it state, comes in, you might take multiple actions to get multiple states. There's multiple, multiple observations and multiple actions that you have to take. And you might eventually get some reward. Your goal is to maximize this long-term reward. So you want to think of RL as multiple actions, multiple steps. LLM adaptation is also something that's very common to make models more interactive. You might have some model that was supervised in nature, X, Y. So X predicts Y, just a category or a number or classification. You can start adapting LLM so that your model can output something in language. Right? And that can be very useful because now instead of just predicting whether it's a cat or dog, you could then maybe ask follow-up questions, right? What type of cat it was, what kind of dog it was. You can also maybe even prompt the model to explain why it was a cat. So the model could identify that it had 4 legs with different colors and so on. So essentially adding language to the output space by using LLMs makes your model more interactive in answering follow-up questions or even explaining its decisions. Of course, how to do that perfectly, robustly, without hallucinations is still a question. Curriculum learning or active learning. This is a very common paradigm where, let's say you want to have some task Y that's really hard, right? So if you just train a model on Y, the model is going to be terrible. So what you can do is you can first supervise the model with some tasks that are easier, just like how a student learns. A student learns from some curriculum, from easier tasks to more difficult tasks. So how to choose that curriculum is an open question, but there's tons of work on it. Active learning is a similar paradigm where you might first have your data, a model make predictions on easy data, and then based on the current state of the model, you would then go out and search for increasingly difficult data or increasingly difficult tasks for the model to tackle. And finally, human-in-the-loop learning, right? Everything before was mostly just done automatically in a computer. But of course, there's many settings in which you have X to predict some label or take some actions. There's some human feedback that's in the middle of it, which can then be used to train a model for new X's and to make new predictions. So this can be done iteratively to as many loops as you need until you are satisfied with the performance, right? So it can be raw human feedback, or perhaps after you've seen enough human feedback, you can then train another model to mimic how the human gives feedback. And so that can be a way of automating from some human feedback to eventually automating and predicting how the human would give feedback. Okay. So let me just finally go through several other important tips. So we looked at different forms of data, how you should think about the properties of the data you're collecting, different learning paradigms to learn from data, and finally a learning process. So essentially the whole goal of machine learning AI is to find a good way to model, to learn relationships, to learn features from your data. And oftentimes you consider a model or a class of models. So a class of models could be a class of neural networks, a class of LLMs, a class of linear functions, a class of decision trees, and so on. So this, for example, just in one dimension, if you have X, you have Y, you have some data with both X and Y labeled. So data and labels, you're essentially learning a function that learns the relationship of your data. Right? So you often see these blocks, right? X comes in, you learn some function F or H, and you make predictions Y. So in the next lecture, we'll look at, essentially how to define these models, what these models look like. How well your model basically performs really depends on how you choose the model, or how do you define the parameters of the model. But before diving too much into the model itself, how do you even evaluate how good a model is, right? So there's this often problem that you see called overfitting versus generalization. The real goal is to generalize to future data. In machine learning, we talk about all this data that you've collected. Let's say you collected a bunch of images and you've labeled them for different objects in it. You're essentially training a model on that data, but your hope is to generalize to new data, right? If I take a photo of a new image tomorrow on my camera, I want to be able to make that prediction. If I have someone interacting with my LLM, tomorrow or a year from now, I want the LLM to do well on that interaction. So there's risks. Sometimes the model doesn't even capture the relationship. So if that's the X and Y relationship over there, you learn this function that's called underfitting, so it's not learning the relationship well, your model won't work well, and if it's really capturing the relationship too well, we call that overfitting. So it's already specialized to your training data, and it might not generalize to actually when you deploy the model on test data. Right, so this blue curve is clearly overfitting and fitting too well to the training data instead of actually capturing a smooth relationship. So that's a worry. And generally in practice, you would collect your data, you would split it into training, validation, and testing. This is meant to simulate this notion of collecting data to train on before testing on new data. And you're essentially training a model on a training set, validating and tuning hyperparameters on a validation set, and measuring how well a model does on a test set as a mimic for how the model will do on true future data, which you don't have yet. Okay, and of course, it's critical to make sure your test data conditions match as closely as possible to the conditions in which you want to actually deploy the model in the real world. All right, so summary, how to data. I'm going to end every slide with how to something, but this theme was data, so how to data. Firstly, decide how much data to collect and how much to label. Assuming that you are going to collect labels. While taking into account the costs of collecting data, the cost of hiring human annotators to label the data, and monetary costs, time costs, and so on. Clean data, usually there's some normalization or standardization of your data that you need to do so that everything fits into a good range. Find noisy data, detect outliers, anomalies. There's all packages to do this. Visualize your data. Not many people do this enough, but you want to plot it, right? If this is x1 and this is y, I plot it. I know that I'm looking for a linear relationship between x and y. So that gives me an idea of what model to design. This is a 1D, so it's easier to plot what if the data is in higher dimensions, and there's ways of doing dimensionality reduction called PCA, TS&E, to basically identify the clusters, right? Do my data even fall into the clusters that I want to predict in the first place before I design any model on them? Decide on evaluation metric. What is a good way to evaluate how good a model is, whether it's something like a square error, you're doing prediction of a continuous value, whether it's a classification error, or maybe something more involved like a user study or usability test. Typically, you also want to look at proxy metrics and real metrics. If your real metric is how a human uses it in the future, but you don't want to iterate with humans when you're just designing a model, it can be useful to get some proxy metrics, which are approximations of the real metric. And of course, these metrics can go quantitative and qualitative. And then and only then you would choose a model class, learning algorithm, and do the machine learning. So no starting with this. 1, 2, 3, 4 needs to be done first. All right, so to summarize, looked at several examples of common data modalities. We give a unified scoping framework on how we can think about the dimensions in your data. We looked at types of data, labels, and learning objectives, and also challenges with, for example, overfitting, underfitting, and actually generalizing to real-world examples. So assignments for this coming week. So no reading assignments yet. That's going to start, I think, next week. Make sure you fill in your project preferences form by today to give us an outline of what tasks and data and teammates you're looking at. If you haven't found a team yet, please, maybe go outside and mingle and try to find people with similar interests. The project proposal presentation to be next Thursday, roughly 5 minutes per team. We'll give out the instructions. And for this Thursday, we're going to have a tutorial by some of my students on ML tools and practical tips for training and debugging the ML pipeline. All right, folks. And for today and Thursday, if you want to meet about the projects, I'll be in my office, save some time from 2 to 3 today and 2 to 3 on Thursday, so we can discuss your course projects if you need any feedback on it. All right, thanks, everyone.